Hello students. In this video lecture, we'll be taking an example of a simple heat transfer problem. We'll try to solve this heat transfer problem based upon both the methods, that is finite difference method and shooting method, and then we'll see what's the comparison of the results of both the methods. And of course, we'll know that shooting method is a bit lengthier and a lengthier to solve, but the solution, the methodology, the solution remains the same, whether we approach by finite difference method or by the shooting method. And secondly, we'll take another problem of finite method, where we'll be discussing a mixed boundary problem, that is a Robin mixed boundary problem. Clear? So let's take the first example. Now over here we have a problem with us, that there is a convection occurring in this fin tube which is connected with the wall. The wall is maintained at a specified temperature Ta, and the length of the fin is L, and we have at the x equal to L, we have a bond, the other temperature, that is Tb, present over here. The heat is being lost from the fin to the surroundings, and the surrounding temperature is Ts. So the heat convection which is occurring to this fin is represented by this differential equation, that is d square T by dx square minus hcp by kac into T minus Ts is equal to A, where all these parameters are given, that hc represents the heat transfer coefficient, P is the parameter of the pipe, K is the thermal conductivity of the fin material, and AC is the cross-sectional area of the fin. Plus the parameters are given, that the total length of the pipe is 0.1 meter, T naught, that is at the surface over here is given as 473 Kelvin. Temperature at 0.1, that is at x equal to L, it's given as 293 Kelvin. The surface temperature is given 293 Kelvin. So these parameters are given. So let's try to solve it by first finite difference method. Okay, so I'll just move it up. So the first method which we'll be solving is finite difference method. Now in this we substitute the values of all the parameters which are given to us: hc parameter, AC, and area. So if we substitute these values, the value of this term comes out to be, so the differential equation is 166.67 into T minus 293. Clear? Now further, there's a given condition over here. Okay, nothing is given, so it depends upon us that how much division of a fin we want. Let's take if this is x equal to L0 and this is x equal to L. So let's divide into 4 parts. So then this is equal to x equal to L by 1, 2, 3, 4, 5, L by 5, 2L by 5, 3L by 5, 4L by 5, and L. Clear? So the total length is 0.1, and we have 5 sections. So the H is L by N, which comes out to be 0.0. So the step size is 0.02. Clear? Or we can say I equal to 1, I equal to 2, I equal to 3, and I equal to 4. Now we're going to convert this into the finite difference one, that is Ti plus 1 minus 2 Ti plus Ti minus 1 over H square minus 166.67 into Ti 293 equal to 0. Upon simplifying, what I have is ti plus 1 minus 2ti excuse me 166 minus 67 h square 293. Upon simplifying, what we have is so this is our main equation. Now we put I equal to 1. So we have t2 minus 2.0667 t1 plus t0 equal to 19.53, and t0 is given as how much? 290, oh sorry, 473. So the equation reduces to 492 534. That's equation number 1. Equal to 2 t3 2 I equal to 3 19.5 number 3 4 and t5 is given as how much? So we have that's equation number 4. So we have 4 equations, 4 unknowns, all are linear equations. So we have a matrix. So first equation, that is t1 t2 and this one. And the second equation, 1 this and this, so we have 1 from the say third one, and then from the third one. So upon simplifying, we have the values of t1 t2 and t3 t4. So yes, let me show you how we can use Excel to solve this 4 by 4 matrix, because normally in a calculator we can solve 3 by 3 matrix, but since this is 4 by 4 matrix, the inverse of this becomes quite difficult to solve. So we can use Excel also to solve this thing. So let me show you an Excel. So we open up an Excel and we represent the matrix over here. We have 1, then we have 0, 1. Okay, that is not there. And then we have 0, 0, 1, and yeah, this is the matrix. And then we can write the other values over here. Minus 492.534 minus 19.534 minus 19.534 minus 312.534. So we have this. Now we need to take the inverse of this matrix. In order to take the inverse of this, since this is 4 by 4, so we'll first select 4 by 4, and then we're gonna put equal to, and then we put this condition command over here, that is m inverse, and then select the array. So we'll select this array. Once we select the array, we close this, and then do not click enter. Then you will have a different answer. Okay, let me show you. If you put an end, if you click an enter over here, you will have this thing. So this is wrong. So we need to delete it. Select again 4 by 4. Then again write m inverse. Select the array. Close this one and click Control Shift Error in one go. Control Shift Enter. So you have, okay, I've done a mistake over here. Since now let me select again. Yes, now this is 4 by 4. Yes. M inverse the array and enter, and then Control Shift Enter. Yeah. So this is the inverse of your matrix. Now once the inverse matrix is there, now multiply this inverse matrix by this matrix, so you will have the solution. So for this also, select 4 by 1 column equal to, there is another command, m matrix multiple. So in the first array we'll put the 4 by 4 matrix, comma, then we'll select the other array, close the bracket, and then again Control Shift Enter. So we have the solution with us, that is 420, 834, 888, 48, 850, and 320. So this is the solution which you get. So the temperature T1 is 424.4, T20, T2 is 384.55, T3 was 350.83, and T4 is 320.98. So this is how you can use finite difference method along with the Excel to solve. If we have 4 by 4 matrix, we can have 5 by 5, we can have 6. And so depending on those matrix size, the number of equation increases, the number of variable increases, and you can use Excel to solve that matrix. Otherwise, if it is 3 by 3, so you can easily use your calculator to solve it. So this is how you can use finite difference method to solve this. Now, second method is we're gonna use the solve the same problem now by shooting method. Shooting method. And shooting method will first come across the same equation. So putting all the values of these parameters, so our equation is somewhat again same. This is 0.67. So dt by dw or dx will be represented as w, and the other equation will be dw by dx equal to 166.67 t minus 293. So we have two equations. The initial condition was at x naught was 0, t naught was 473. So our first guess of W naught. Let's take a first case somewhere around 3000, minus 3000. So we'll apply RK4 method first to solve for that system. So H is again taken as same. So why we're taking H as same? So once we have the solution, we can see, we can compare the results. So K1 is H times F of the first function. Let's say this is F. We can take this as G. So we have H of function evaluated at X naught, omega naught, and W naught and D naught. So K1 comes out to be minus 60. Similarly, L1 is H times G at X naught. So L1 comes out to be 0, 1. Similarly, K2, K3, K4 you can calculate. L1, L2, L3 and L4 you can calculate. For K2 you have H of H by 2, L1 by 2 and D naught plus K1 by 2. Okay, so I have already calculated these values. So K1, K2, K3, K1. I just give you the values of K1, K2, K3, K1. So K2 comes out to be minus 54, K3 is minus 55, and K4 is minus 49.8. Whereas L2 is 500.01, L3 is 510, and L4 is 420 points. So using K1, K2, K3, K4, your value of K is minus 54.63 and the value of L is 506.68. We know how to calculate this. This is nothing but 1/6 of K1 plus twice of, and similarly you can calculate L also. Clear? So I've given you this value. So at first iteration, that is at X, omega naught and T naught. Okay, not omega naught. We'll write omega and T, W and T. So when this was 0, this we have assumed as minus 300. So this is 493 at point 2. This is minus 2493.32. This is 418.37 at point 4. This is minus 2153.89 and this is 372.15.6 minus 1958.93. This is 331.24 and this is point 0.8. In fact, 0.0. I'm making a correction. 0.02, 0.04, 0.06 and 0.08. So it is minus 18, 292. And when this is point 0.1, minus 1958.8. This is 254.58. Now we can clearly see at T equal to 0.1, it should be 293 Kelvin. But by considering this as the guess value, the assumed value, we have temperature at point 0.1 as 254. So now we need to again repeat the same process for another value of omega naught. Let's say this time we take it as minus 25. Again repeat the same process and check the value of temperature at point 0.1. Clear? So again the same using RK4 method. So do that. I've already calculated those values. I'll just give you the values so you can try at your places and cross check the solution. So when it is 0, this is minus 2500 and the temperature was 473. So when this is 0.02, this value comes out to be minus 9 0.67, and this is 428.48, and this is zero point 0.4 minus 1585.98, and this is 393.05. Basically all this becomes quite lengthy in calculation. You can see, so 0.06, 364.33, then it is 0.08, it is 1104.57, we have 3.4, and once we have zero point 0.8 we have minus 981.369, and we have 319.65. So now you can clearly see with respect to uh, initial of minus 2500, t at point 0.1 is 319.65, whereas it should be 291. So using linear interpolation, we can calculate the actual value of omega. So at omega of minus 3000, temperature and point 0.1 is 254.58. At minus 2500, this is 319.65, whereas I need 293. So correspondingly I can find out the value of this. So using linear interpolation, that is, let's say this is m, so m is minus 3000 plus the difference of this, correspondingly the difference of their values, into the difference of these values. So m value comes out to be minus 2704.78. So that means our assumed value, should be minus 270.70. So now we're gonna repeat the same third time RK4 method using the assumed value of WS minus 2704.78. So I've already calculated it, so you can note down the values. Clear? You can try at your places those values. So when x is 0, this is minus 2704.7, the assumed value, and the temperature was 473. So when this is 0.02, this becomes minus 2188. Okay, 2188.3. This is 424.3. And this is 0.04. It becomes 1818.5. This becomes 384.5. When this is 0.06, it's minus 1570.8 and 350.78. When it is at 0.8, this is minus 1428.4, this is 320.95, and when it is 0.1, this is minus 1381.8, 293. So these are the temperature values corresponding to these positions. So you can clearly cross check your solution. This is what we have from shooting method, and by finite difference method we have the results as, if you already noted it down. Okay, those results are for, so 473, it was 424.39, it was 384.55, 350.83, 320.98, and we have to. So you can clearly see the results. So there's hardly any major difference in the calculation part of result part of the either we approach by shooting method or by finite difference method. The only difference between both the methods is the shooting method becomes quite lengthy in calculations. Otherwise, it gives the same result as we have it for finite difference method. Clear? So you can approach any method, any problem by either of these methods. So let's take the second example where we'll try to solve a mixed boundary value problem using finite difference method. So we have Robin mixed boundary conditions. Suppose we have an equation with us that y double derivative minus y minus 1 is equal to this, and y at 0 is 0. These are the boundary conditions. And the other boundary condition is y dash at 0, sorry, y dash at 1. The other end of the plus y at 1 is equal to 1. So let's say we have a length from starting from 0 to 1. So over here at this end we have this condition, and at this end we have this condition. Now let's take n as 4. So this is I equal to 1, I equal to 2, I equal to 3, I equal to 4. So the step size is 1 by 4, that is 0.25. Let's try to solve this thing. Now first equation is this. So yi plus 1 using finite difference method minus twice of yi plus yi minus 1 over x square minus yi equal to 1. Rearranging, clear. So this is from the, now we have the boundary conditions. The first boundary condition is yi is 0, so y at 0 is 0. Second boundary condition was y dash at 1 plus y1 is 1. So y dash, first of all we calculate y dash. Let me write it over here. Yes. Now y dash is yi plus 1 minus yi minus 1 over 2h plus yi is equal to 1. So upon solving this thing we have now for y dash 1, if you look at this partition over here, if you look at this condition, this is I equal to 0, I equal to 1, I equal to 2, I equal to 3, I equal to 4. So over here I will be equal to 5. So now put I equal to 5 in this equation. Then only we'll have this condition at 1. So put I equal to 5 over here. So we have y, not y5 or y6. I think I equal to 4 will work. Let me check. Okay. I equal to 5, 4. Okay. I equal to 1, 2, 3, 4. So I think somewhere we have made a mistake or what? Let me check. Let me check. We have I equal to 1. We have I equal to 2. I equal to 3. And for I equal to 5, 4. Okay, no. Let's keep it as it is. Let's not disturb this thing. Let's not put any value. Let's keep it as it is for the timing. Let's name it as equation A. Let's not, put any value of I. Now, our main equation is this equation. Let's try to first solve it. In this equation, that is equation A, let's name it as equation B. This is equation A. From equation A, put I equal to 1. So what we have is y2 minus 2 plus h square y1 plus y0 is h square. Now y0 is 0 and h value is, we already know, is zero point 0, how much? 0.025. So put all those values. So we have equation as y2 minus 2.0625 y1 plus 0.062. First, I equal to 2 by 3 0.0622. I equal to 3. We have by 4 by 3 plus 0.062. Since we have 4 divisions, so we need y1, y2, we have y2, y3 and y4. So these are this thing, and this is basically y5, and this is y0. Y0 is given and y5 is given. So there are 4 unknowns. So there are 4 equations we have already derived. 3 equations we derived. For fourth equation, put I equal to 4. So that we have is, once we put I equal to 4, we have 5.50625 by 4 plus y3 as 0.0625 fourth equation. But y5 is the point at which we have already the boundary condition available. So for value of y5, we put I equal to 4 in equation B, that is in this equation. So put I equal to 4 in this equation. So we have y5, which is equal to, solve this thing, 0.5 plus y3 minus 2h y4. So we have the value of y5, that we will substitute over here in order to reduce it into 4 parameters only. So once we substitute over here, what we have is finally is 0.5 plus y3 minus 0.5 y4, that is for y5, minus 2.0625 y4 plus y3. So upon simplifying this thing, we have twice of y3 minus 2.5625 y4 equal to minus 0.0437. So that's your, basically your equation number 4. So we have 4 parameters, we have 4 equations, all the parameters are linear, so we can prepare a matrix. 1 0, so 0 minus 2.0625 1 0 0 2 and minus 2.5625 into y1 y2 y3 y4, and we have 0.0625 0.0625 625 and minus 0.4375. So again you can use Excel to solve this thing. So what I'll do, I'll just show you what I've done is, we have a matrix table with me. I'll just simply replace the values in this main matrix. So let me put it as this thing, right? Different color, this as the different color, and finally the result will be shown over here with a different color, that is, let's mark it. So I'll simply replace the values over here. So minus 2.0625, 1 is here, okay. Minus 2.0625 minus 2.065, we have 2, and minus 2.565. Okay. Now we change these values, 0.065, 0.065, 0.065, and we have minus 0.4375. So these are the values which we have. Clear? So it's quite easy, just change the parameters of the Excel and get the result. So the value of y1 is minus 0.0354, y2 is minus 0.0105, y3 is 0.0764, and y4 is 0.23%. So that's the solution. So this is how you solve, mixed boundary value problem, also using your finite difference method. You can also use to solve the Excel for the matrix of bigger size of 3. Okay, so that's it with this problems of mixed value problem, and we have solved another problem using where we can either use finite difference method and shooting method. Thank you so much.